All right, so today we're going to look at section 2.4, which is on solving linear inequalities. Okay, we'll do a little bit algebraically, review the rules, especially when you have to flip the inequality. And then we'll do some graphically, okay, on the calculator. Okay, so there's 4 basic inequality symbols. Can somebody remind me what or maybe at least just give me a couple of the symbols? Adrian?
Greater than or equal to.
Okay, so you got greater than or equal to. And what are the other 2 symbols? Luke?
Less than or less than equal to.
Yeah, less than or equal to. Okay. Does anybody need me to label which symbol is which? Okay, the less than kind of looks like an L, kind of bent in. So your less thans. And then your greater thans, well, those are the ones that point to the right. Okay, these are examples of inequalities. Okay, the first one is an inequality that's always true. 3 is less than 8. And similar to when we solve an equation, if you ended up with something like this, that's a true statement. And it's it's like an identity for inequalities. So if I had 2x plus 3 equals 2x plus 8, and I subtracted 2x from each side, I would get exactly what I have right there. Okay? I'd get 3 is less than 8, which means this inequality is always true. Okay, so if you solve an inequality and you end up with a true statement when you're done, the answer is all real numbers. What happens if you solve an inequality and you end up with a false statement when you're done? Like if you subtract 2x from each side here, you get 30 is less than 8. What does that mean?
Undefined.
It's a false statement.
It's a false statement, which means the answer is no solution. Yep. And if you look at it just logically, you can never double a number and add 30 and have that be smaller than doubling the same number and adding 8. Doubling and adding 8 is always smaller than doubling and adding 30. Okay, so that one's impossible to solve. Okay, and this inequality, 3x is greater than 12. That's a conditional inequality that is true for any value from a certain number on. Okay, so if you pick numbers larger than 4, you would have a true statement. If you pick numbers smaller than 4, those would be the numbers that are not solutions. Okay, you'd have to pick numbers larger than 4. And the way you figure out if a particular number is a solution, okay, all you have to do is plug it in, see if you get a true statement. All right, so let's look at this one. And let's say I asked you if -5 was a solution. Okay, is -5 a solution to that inequality? No, because if you plug it in, you get 3 times -5 is -15. -15 is not greater than 12. Okay, what about 4? Is 4 a solution? A couple people say yes, no. How come?
It's not greater than 12, it is 12.
Right. If you plug in 4, you get 12 is larger than 12. That's not true. All right. How about if I plug in 6? Is that a solution? Yeah, because now I have 3 times 6 is 18. 18 is greater than 12. All right, so that's how you check if a number is a solution. Plug it in, see if you get a true statement. All right, when we talk about inequalities, there's 2 special types that come up. Okay, one of them is conjunctions. And does anybody know what word you can put between 2 inequalities and it makes it a conjunction? Or is actually the other one. That's a disjunction. But it's the other one we're thinking of? Not if. If is used a lot when we have logic, like in geometry. If it's raining out, then it's not sunny, like those kind of things. But we're not using if here. And. Yep. So 2 inequalities connected with the word and. That's a conjunction. Okay. this is an example of a conjunction. X is greater than negative 1, and X is less than 3. So what is that kind of like saying? If you wanted to describe all the numbers that are solutions to this, bigger than negative 1 and less than 3, what's another way to say it? Yeah?
Any numbers between negative 1 and 3.
Exactly, it's just between. Okay? We have to be careful, is it strictly between, meaning can I include negative 1 and 3, or is it not including? In this case, it's not including negative 1 and 3. Okay? And you can also combine this into a single statement. Does anybody know how you do that? You start with X in the middle, and then we go from there. Yep.
You say X, and then on the left side you would say have the is greater than negative 1.
So greater than negative 1, yep.
And on the right side you say but less than negative 3.
Yeah, exactly. So you can combine a conjunction that's separate, two separate statements into one, just like Luke said. That's not the only way to do it. You can flip everything around and do it this way. Okay, I generally don't do it this way, but technically that's the same thing. Okay, it says X has to be less than 3 and greater than negative 1. When you write it in either one of these notations, you don't need the word and. Okay, and is kind of built into that, that notation. Okay, if you want to write it as two separate statements, then you got to put the word and. Okay, so because we're talking about a set of numbers between two numbers, we call that an interval. Okay, specifically, this is called an open interval. Okay, so I'm going to talk a little bit more about what that means. But basically, an open interval has to do with these symbols. And specifically, this kind of interval has numbers for its low limit and its high limit. We don't always have numbers for the low limit or the high limit. Okay, think about some other things we've done that maybe we don't have a number in one spot. We have something else. So we'll talk about that in a second. But as long as you have numbers for the lowest value and the highest value, that's called a bounded interval. Okay, so bounded interval means your lowest number and your low limit and your high limit are actually numbers. Okay, and there are 4 types of bounded intervals. Okay, you can have what's called a completely closed interval. Okay, closed means you would have a bracket on each end. And all that closed means is you can actually include the endpoints of your interval. Anybody think they can tell me another type of bounded interval besides fully closed? Luke?
Half closed.
Okay, we'll talk about that one. We could have a half open or half closed. And there's one more type.
Open.
Yeah, a fully open interval. Okay, open interval would have a parenthesis on each end. And the parenthesis indicates that you cannot use your low limit or your high limit. Okay, you can approach them, but you can't reach them. Okay, and as Luke said, you can have a half open interval. Specifically, this one is half open on the right, and you could also have half open on the left. Or you could say half closed, but either way. Okay, so those are the 4 types of bounded intervals you can have. Okay, on page 99, they show you some pictures. Okay, if you want to see them, I'll draw a couple of them. So So for an open interval, that would look something like this. It's a between, but you're not including A and you're not including B. Okay, strictly less thans. Okay? No equal tos. If you were graphing it on a number line, there's two ways we can do it. We can either use an open circle on A and an open circle on B and shade between. Or what other symbol can you use in place of the open circle? And we're using it in the notation on the left. Yeah, you could use a parenthesis. So that's what an open interval looks like if you draw it. Okay, and let's see, half open. I'll do one more. That would look like this. We can include A, so I put the equal to, but I cannot include B. Okay, and in a sketch, mark A, mark B. It's going to look almost the same, except what's the one thing I would change in the picture? Yeah, Jack?
Brackets.
Yeah, where would I put a bracket?
To the left.
On the left one. Okay, bracket on A, still parenthesis on B, shade between. Okay, and if you want to see the other pictures, you can just look at page 99. Okay, any questions on those four types of bounded intervals? All right. So if we can have bounded intervals, we can also have unbounded intervals. So I said to you, think of an interval that doesn't use a number for one of its bounds. Well, the only other thing we've used besides numbers is an infinity symbol. Okay, infinity symbols, when you put it either as the lowest you can go or the highest, makes your interval unbounded. There is no number that's a limit. Okay, so these are all the different ways you could have unbounded intervals. Okay, you could be unbounded on the left, and then closed on the right or open on the right. Or you could be unbounded on the right, and closed on the left or open on the left. Okay, but that's it. It's the only way you could have an unbounded interval on one end. If you wanted it unbounded on both ends, then you could have something like this. Okay, and then the only difference in the sketch is when you do something on a number line, like let's say you wanted to shade from 5 to infinity. It doesn't stop, so we put an arrow to indicate it just keeps going. Bracket on 5, shade right. Okay, this one would be parenthesis on 5, but we would still shade to the right. Okay, and we're going to practice writing some intervals right now. But any questions on unbounded intervals? All right, so let's try this one. Okay, they want us to take this interval and write it as an inequality. Okay. Anyone think they could tell me how to write this interval as an inequality with x in the middle? Luke?
X is greater than -3.
So we got the greater than -3.
But not including -3. And,
Not including it, yep.
and it's less than, but or equal to 5.
Perfect. That's how you write it as an inequality. Okay. Anytime you see an interval that's bounded, two numbers, it's always a conjunction. Okay, they're saying between these two numbers. Just be careful, is it between including the endpoint or not including, or a mixture of both? Okay, let's look at this one. But Jacob, what kind of interval is that?
Half open.
Yeah, I agree. It's definitely half open. Could somebody else give me another word to describe it? It's half open and Bria? And it's unbounded. Unbounded because there's no upper limit. Half open because of the parenthesis on the right. Right. How would I write that as an inequality? Yep.
Only have to write one thing, is that is x is greater than -4.
Yeah, this is not a conjunction. Okay. All you have to do here is x. Now you said greater than? Greater than or equal to -4. And that's it.
Why do you have to do that?
Because you want to include every number from -4, including -4, up to infinity. Okay, whenever you have an unbounded interval, you don't need to write it as a conjunction. Okay? Some people say, well, could I do this? -4, infinity, x in the middle. Technically, you could, but all you really need to say is it's greater than or equal to -4. Okay? You don't have to say it's less than infinity. Everything's less than infinity. Yeah?
It's unbounded if it has no lower limit to it.
Yeah, it's unbounded if you have infinity anywhere in it. Yep. Okay, questions on that one? All right, let's try this one. C. Okay, what kind of interval is that? We'll start with bounded, unbounded, and then tell me if it's open or closed or a mixture of the two. Yep. It's bounded and closed. Okay, in a second, we'll ask ourselves, do we really need to say both of those terms, or could we really just say one of them, and it might automatically answer the question? But yes, bounded and closed. Okay, put my x in the middle. And Nick, how would I write this as an inequality?
You write -8
Yep.
is greater, less than or equal to,
Good.
and then x is less than or equal to -3.
Perfect. Okay, you always put the smaller number on the left, or the more negative number, the number that's more positive on the right, and have both of your inequality signs point to the smaller number. And -8 is less than -3. It's smaller. All right, so could you have an interval that's unbounded and closed? No. Why would that be impossible to have an interval that's unbounded and closed? Yep.
There's no possible way to reach negative infinity or infinity.
Yeah, you can't reach negative infinity or infinity, so you'd never put a bracket on infinity. And if you don't put a bracket, you got to put a parenthesis, which makes it open. All right. So if we go back to some of these examples, if in example C, okay, Bria said that it was bounded and closed. If you tell me that it's fully closed, does that mean it's automatically bounded? If you have an interval that's closed on each end, does that mean it's bounded? Yeah?
Yeah.
Yeah. Closed means you have a value you can reach. Okay? If you can reach something, it has to be a number. And if you have numbers, it's bounded. So if you tell me it's fully closed, I automatically know it's bounded. What if you tell me it's fully open? Do I know that it's automatically unbounded? If you tell me that it's a completely open interval. Does open mean unbounded?
No.
No. Here's an example. Where do we have them? Right. Something like this. Okay. If I put 2, 5. That's an unbounded interval. I'm sorry, it's an open interval, but it's not unbounded. Okay. So sometimes you have to think a little bit about the terms, but think of the different combinations you can have or not have. All right. All right, so let's try doing a few graphs. Okay, x is greater than or equal to 2. Well, first thing, I just got to number my number line a little bit. Okay, you can number it however you want as long as it's consistent. Okay, just, if you go by ones all the way. Okay, and Curtis, how would I graph x is greater than or equal to 2?
You would put a bracket on 2
Yep, bracket on 2.
going to the right.
And going to the right. Perfect. So bracket on 2, shade right. If you didn't want to use a bracket, what other symbol, Brad, could you use?
Could use a
That means the same thing.
solid dot.
Yeah, you could use this filled-in circle, the solid dot. Yep. Okay, but I'm just going to use the same notation that we use when we write integrals. Okay, before we do that one, is that a conjunction? X is greater than or equal to 2.
No.
Okay, no, that's not a conjunction. Okay, this is actually a disjunction, if you think about it. X is greater than 2, or x equals 2. This basically means this. We normally don't write out a greater than or equal like that, but you could. X is greater than, or x is equal to 2. Okay, x is less than 5. Okay, how about Ethan? What kind of symbol would I put on 5? And which way does it have to face? Yeah, it's going to face left because that's the way we shade. Okay, so x is less than 5. Any questions on that one? Okay, Shannon, is that one a conjunction?
Me?
Yeah.
I'm Lauren.
Lauren, I'm sorry.
Okay, and no.
No, that's not a conjunction. Okay, that one's not even a disjunction because it doesn't have the equal to. It's just x is less than 5. It's just an inequality. That's all you can say. All right, how about C? Sam, is that a conjunction?
Yes.
Yeah, that's a conjunction because it's telling us to be between those two numbers. All right, so John, what kind of symbol would I need on -1?
A bracket.
Yep, bracket. I also need to put some labels on my number line. So let's do that. Okay, and how about James? What kind of symbol on 3?
Let's see.
Yep, put a parenthesis. Okay, and Denver, where do I shade? Yeah, we're going to shade in between. Okay, everything greater than or equal to -1, but also less than 3. And Brad, if you didn't want to use the parenthesis, what could you use in place of that? An open circle. Hey, any questions on graphing inequalities? All right. So when we're solving an inequality, you basically use exactly the same steps you use when solving an equation, except one thing you got to be careful with. John, do you know the one thing you have to be careful with when solving an inequality?
Making sure that it's going to be that it's actually going to be true, like a true statement.
Okay, so we want to make sure, like if you were checking an answer, you mean? Yeah, if you're checking an answer, you should always come out to be a true statement. But how about as you're going through solving it, before you even get the answer? Something you have to be careful of in the steps. And you don't have to be careful with this when you solve an equation. This would never happen. Yep?
Isn't there like a flip that you have to do that like ends up flipping like the negative sign or something?
sometimes you have to do some kind of flipping thing. Does anybody remember what you might need to flip and when you have to do that?
You divide.
When you divide by a what?
A negative number.
A negative, or if you multiply. Okay. So basically, if you multiply or divide by a negative, flip the inequality. Okay, so if you multiply or divide by a negative, flip the inequality. Now, sometimes as you go through a problem, if you do the steps kind of clever in the right way, you can avoid having this situation come up. Sometimes you can. Okay, if I gave you a problem like this, there's not much you can do to avoid the negative in front of the x. You're going to have to deal with it. But in this problem, I think you'll see as we go through it, you might be able to avoid a negative in front of x. Okay, so follow all the same steps, just as if you were solving an equation. Okay, so Ryan, what would my first step be here?
Distribute.
Good, I'm going to distribute, and can you tell me what I get when I do that?
3x minus 3.
Yep, 3x minus 3, and then we're going to add 2. So what does that give me?
Negative 1.
Yeah. So I did the distributive, and I combined like terms all in one step. Okay, Austin, what could I do next here?
Minus 3x.
Yeah, I would do it that way. Why do you think I like that way better than minusing 5x?
Avoid negatives.
Yeah, if you do it this way, you can avoid at least a negative in front of the x. So that's gone. I'm not saying you're going to be able to avoid a negative everywhere, but at least in front of x you can. Ian, what would I do next?
And you're going to have to take away from 6 and negative 1.
Yeah, we're going to take away 6 and take away 6. Adrian, do you have a question?
No.
No? Yeah.
Would the negative 1 that was in the parentheses also be multiplied by 3?
Yes, it was. But then we added 2 to it.
Oh.
So it's not that we didn't do the distributive, it's just we did negative 3 and then plus 2, and that gave me negative 1. So it might be better if we show that out in 2 steps. All right, so 6 minus 6 is gone. Negative 1 minus 6. And my last step, Nick, what's my last step?
Yeah, divide by 2.
Divide by 2. Now, should I flip the inequality? Yes? How come?
I don't know.
Not sure. So anybody agree or disagree? General thoughts? Yeah.
You don't flip it because you didn't divide by a negative?
What about this negative on the other side?
Or you didn't divide by.
Exactly. I didn't divide by it. Okay, I divided by a positive 2. Okay? Even though there's a negative on the other side, don't worry about that. If you divide by a positive 2, which is what I did, you don't have to worry about flipping. So I end up with negative 7 over 2 is less than or equal to x. And it's okay to write the answer that way. I wouldn't mark it wrong. But can anybody tell me how you would write it putting the variable on the other side? And the reason, well, I'll ask you maybe why you think I like the variable on the left. Yeah?
It's just like the correct way to do it. Do you want me to say the answer?
Yeah, why don't you say it first and then you can tell me why that might be better.
It would be x is greater than or equal to negative 7 over 2.
Perfect. Okay, now why do you think I prefer it that way? That's something to maybe do with graphing.
Because the variables first.
Okay, the variables first. And how does that tie with graphing? Look at the symbol and think about if you were to graph that. Why do you think this way, I think, makes it easier to graph? Well, which way would you be shading if you were to graph that? To the left or to the right?
To the right.
Yeah, you'd be shading to the right. So Now, does anybody see why I like the second way better?
No,
No?
no, I'm lost.
Everyone sees these are the same thing, though.
Yeah.
Okay, so I'm just wondering, why might I like that second way better, especially if I'm going to graph, something you can remember? Yep?
The inequality sign shows which way to like shade.
Yeah. Okay, if you're going to, if you forget which way to shade, as long as you always put the variable on the left, the symbol always points which way you should shade. If you put the variable on the right, then the symbol points in the opposite direction you should shade. Okay? So that's why I prefer it with the variable on the left. Okay? Always tells me which way to shade. All right, so we've done a little bit algebraically. Let's look at using the calculator. Okay, so one way to solve these on a calculator is doing something we've already done before. Get 0 on one side, graph it, and then find the root. The only difference is the root isn't going to be your answer. It's either going to be everything above that root or everything below the root. Okay, it depends on if it's a less than or greater than. Okay, so what would I have to subtract from each side to get 0 on the right? Jack?
2.
Yeah, subtract 2, and I get this. Okay, that's what I'm going to graph. And I'm going to look for where that graph is below 0. Okay, where is it below the x-axis? Okay, so let's graph it. Get rid of anything else I already have in there. Okay, type in 4x minus 3. And I think if you do zoom, just 6, a standard window is going to be fine. So I want to know where this graph is below the x-axis. So the first thing I need to find is the point at which it exactly crosses the x-axis. And yep, so find the x-intercept. Okay, pick a point to the left, to the right, and do your guess. And this crosses the x-axis at exactly 0.75. So now, do I want values less than 0.75 or more than 0.75? Less. The values that are less are all going to give me the ones that go below 0. If you go more, you're going to be above 0. Okay, now do I want to include 0.75 in the answer or no? No, because it's strictly less. Okay, so the answer is everything from negative infinity up to and not including 0.75. Okay, that's the first method on the calculator.
Could you go up?
Okay, any questions on that first method? Okay, the second method is basically leave it the way it is. Don't rewrite it. Leave what's on the left, leave what's on the right, and graph each side separately. Put what's on the left in y1, put what's on the right in y2. And now, since I'm graphing two things, I'm not going to look for a root. I'm going to look for where these two things do what?
Intersect.
I'm going to look where they intersect. So now you calculate an intersect, and then determine, do you want all the answers above your intersection point or below? Okay, so I'm going to do the same problem again. I'm just going to do it using method 2. I don't care which method you use. Whichever way is easier for you. All right, so I'm going to graph 4x minus 1. I'm going to graph 2. Okay, 4x minus 1 is in blue. 2 is in red. So if you want to look at it in terms of the color, I'm looking for where the blue is under the red. Okay, so hit graph. Here's my blue. Okay, red one's going to come in. And the first thing I have to figure out is where these cross. And how do I do that? Yep, second calc, intersect. Pick a point on the blue line, the red line, do a guess. And it says they cross at 0.75. Now, do I want values below that or above that? Below. Yeah, if I pick values of x below 0.75, the blue line will be under the red. And that's what I want. Blue less than red. So same answer. Negative infinity up to 0.75. Hey, any questions on doing it as an intersect? All right, so it's pretty straightforward. Okay, sometimes we can have what's called a double inequality, where you've got something in the middle, something on the left, something on the right, and your goal is to get the x by itself in the middle. Okay, the trick with these problems is whatever you do to the middle, you have to do it on the left and the right. So if I wanted to solve this problem, I would divide the middle by 2, the left by 2, and the right by 2. And that would get x by itself. Right? So we're going to do the same thing here. Just try to get x by itself in the middle. Follow all the rules you regularly follow. If you multiply or divide by a negative, both signs flip. Okay, they flip. All right, anybody see the first thing I would do here to start to get this by itself? Ian?
Multiply.
Yeah. Let's multiply by 3, by 3, and by 3. Okay, on the left, that's going to give me negative 9. And should I be flipping my inequality?
No, there is no negative.
Nope, I didn't multiply by a negative. It's less than. Now, what happens in the middle? 2x plus 5 divided by 3 times 3. Yeah, just cross out the 3's. They cancel out. And I get less than or equal to, Lauren, what's 5 times 3? 15. Okay, so that's my first step. Sam, what's my second step? So think about, you're trying to get this x by itself. You got to get rid of the 2 and the 5. Do you know which one you would get rid of next? Yeah, you get rid of that plus 5. So how would you cancel out a plus 5?
Subtract 5.
Yeah, subtract 5 from here. And where else? The negative 9, yep. Anywhere else?
And 15.
And the 15, good. Okay, we've got to do it in all 3 spots. Okay, so Ethan, negative 9 take away 5 leaves me with, yep, negative 14. And John, 15 take away 5?
10.
10. And my last step, divide everything by 2. Okay, Jacob, should I flip my inequality since I just divided by 2?
No.
No. Okay, I divided by a positive. Keep those inequalities pointing the same way. Hey, Brad, what do I get on the left?
Negative 7.
Yep. And on the right?
5.
5. That's my answer. You can write it as an inequality, or you could write it as an interval. I'm going to leave it like that. That's fine. Okay, any questions on that one? Yeah,
Did you put the,
thank you. Okay, any other questions or mistakes that I made? All right, so one of the last things we do with inequalities is absolute value. Okay, so yesterday we practiced solving absolute value equations, and the whole goal was to take and split it up into two problems. Well, pretty much same thing here. Okay, to solve an absolute value inequality, you're going to take and split it into two problems. As always, make sure you've already isolated the absolute value expression. If you've got something like this, you have to deal with that 2 first. You've got to put that on the other side. And you follow all the same rules. Okay? Flip that sign if you divide by a negative at any point in the process. All right. Does anybody remember from yesterday when we did absolute value equations? When you split it up, what's the first one that you split it into? You only really have to do one thing to the original problem. Anybody remember the one thing you have to do? Well, what's our goal? Why are we taking a problem that has absolute values and splitting it into two problems? Why are we doing that? Yeah?
Because you can have either a negative or a positive for like the x.
Okay, and what's going to happen when we split it into two? Something's going to disappear.
The absolute value.
Yeah, the absolute value bars. Okay, so that's the whole goal. So when you have an absolute value inequality, the first one you split it into is exactly the same as the original. Just take out the bars. Does anybody remember what the second one was? You have to take out the bars and you had to do one extra thing. Yep?
Negate the number on the other side.
Yeah. So the second inequality is the same as the original, except you remove the bars, negate the number on the other side, but remember what happens if you make a number negative. Okay, with an inequality, if it becomes negative, you also have to flip the sign. So that's an extra thing we didn't have to do yesterday. Okay, so first one, just take out the bars. The second one, take out the bars, flip the sign, make the number negated. Okay, change the sign of it. Okay, so that's a little bit of an extra step, but really step one is pretty similar to what we did yesterday. Step two, okay, and the last step, this one is a little different. Okay, when you split it into two problems, yesterday we always put the word and between them. So we had x equals something and x equals something. Today we don't always use the word and. Okay. If your original problem has one of these two symbols, you use the word and. If your original problem has a greater than or or equal to, you have to use the word or between your two answers. Okay, and the way I remember which one is which, think of this as like less than. Okay, think of it that way. And then greater. Now you'd be surprised that it works sometimes. Okay, so think of it as greater. Okay, less than, greater. That's how you can remember which one is and or. All right, so let's solve this one. So absolute value expression already by itself. It's ready to split. Okay, anybody tell me the first one I'm going to split it into? And this is the simple one. You don't have to do too much. About Austin?
X minus 3 less than.
Yeah, x minus 3 less than 3. Just take the bars out. Now, the second one, you're going to still take the bars out, but you got to do two other things. John, can you tell me what the second one will be?
X plus 3. No, x minus 3.
Yeah, still x minus 3. Good, flip the sign, that's what we want. And one more thing,
-3.
-3. So you take out those bars, flip the sign, and make it negative. What word should go between them? And? Or should I put or? And. Less than, right? Less than. Okay, whatever works. All right, and now just add 3 to both sides. So x is less than 6, and x is greater than 0. Okay, big difference if you put or in there. That changes things quite a bit. Okay, so you always go back to the original problem. You might look at this and say, wait, that's a great tour, right? Or, no, go back and look at the original problem. Okay, don't look at it after you split it. Okay, any questions on that one? All right, so these are all calculator ones. I'm going to skip over that one. That's pretty much the same type of problem we just did, except it's an or, not an and. So let's go to the last one. Okay, on the calculator. Okay, so are we all going to be okay? So what's okay? So x plus 3 is divided by absolute value of x minus 2. All right, and it says that's greater than 0. All right, so this one it says solve algebraically, but we just did one algebraically. Let's do it graphically. Okay, so let's type it in and see what it looks like. As I type it in, what symbols do I have to use here to make sure the calculator does it correctly?
The absolute variable.
Okay, I definitely need those in the denominator. How about the numerator?
You need parentheses.
Yep. If you don't put parentheses, it might not do it correctly. Divided by math, number, absolute value. You don't need parentheses around the bottom because the bars, they kind of handle that. All right, now we know that something funny is going to happen when x equals a certain number. What would x not be allowed to
It would
be
not
here?
be allowed to be 2.
Yeah, x can't be 2 because then you divide by 0. So something weird is going to happen at x equals 2 on the graph. All right. So we're trying to find out where this is greater than 0. All right, well, I know that at some point, it looks like right about here, it crosses 0. Right? If I pick an x value less than that, it'll be below 0. So I want to know where it is greater than 0. So let's start with this section. How would I find that point right there? Careful, that one's not an intersect. That's a 0, okay? Because we don't have another line to intersect with. So I'm going to calculate the 0. Okay, I'm going to go to the left, maybe. Go to the right, and do my guess. So -3. So I can pick any value from -3, not including it, up to, what's the highest x value I can pick on this section? Forget about this other section for a second. Think about, what did Adrian say we can't use for a value?
Up to, but not equal to.
Right. Okay? I've got this spot here that if I try to equal it, I'm going to divide by 0. So I can go up to, but not including 2. Okay? That covers this section. Now, it looks, at least to me, it looks like this other section is always positive. Okay? The only question is, if I look at an x value really, really big, does it ever eventually come back down below 0? Okay. So what's a big x value I could type into my table and see if it goes below 0 for y?
1,000.
Yeah, let's check what happens when x is 1,000. Okay, I'm just a little bit above 1. Okay, let's check 10,000. Even closer to 1. So it looks like this graph is never going to reach what number? 1. So where is it going to be above 0? I would say this entire section. So that's going to be from 2, not including it, all the way to, what's the highest x value I could pick? Infinity. Okay, so pick any x value from -3 on, except 2. And this graph will always be above 0. This symbol, so I don't know if you guys saw me, but I erased something right here. You can write or you can use this symbol. Have we used that symbol before?
Yeah.
Okay. This symbol means or. Okay. All right. All right. So homework tonight. It's on just one page because we did one section, page 108. Okay, 5 through 7, 10, 11, 14 to 16, 25, 26, 29, 34, 35, 42, 43, 49, and 60 to 62. So again, it kind of skips around a little bit, but we did a few different things today, so I just want you to try like one of each type of thing we did today. Okay, so we'll take a look at that first thing tomorrow. We'll finish chapter 2 tomorrow, and we'll have our test on Friday.